So with task 1 successfully accomplished, we're ready to move on to task 2. And that is the material tuning section. Remember, what we did in class was we constructed this measurement device where the idea is the floating magnet, which is the one depicted right here, is going to reach an equilibrium state when the force of gravity acting on the object is equal and identical to the force that's opposing the object. So this floating magnet could be sitting on a table and it's at equilibrium because the normal force from the table is pushing it up. Or in this case, with the poles aligned, there's a repelling force from the anchor magnet that sits below it that also allows it to reach equilibrium. So when that magnet is in equilibrium, as it was in this case, then it should observe Newton's law, force equals mass times acceleration. We know the mass of the magnet because we measured them in the classroom. We ended up with 3.27 grams. We know the acceleration to Earth, so we're able to calculate the force or the weight of that magnet is going to be 32 millinewtons. So what we're able to do now is cook up a test where we can look at the distance that the magnet actually sits when it's in equilibrium to a number of different cases here. And we had a one stack of magnet, which means there's only one anchor magnet here, and we measured it 5 different times, 5 different samples. So we replaced the float and the anchor magnet 5 different times because there's a statistical variation, and we came up with this number of 7.4 millimeters. So what that means is that the distance between the edge of this magnet, the anchor magnet, and the floating magnet averaged out to be 7.4 millimeters. We also calculated the average between the centers because we already know that the radius of each is 7.5 millimeters, so we simply add 15 millimeters. The 2 stacked case, if you remember, included a second magnet that was attached to the anchor magnet that is out of view. It's behind the first magnet. The same thing stands for the 3 stack case, 4 and 5. So in the 5 stack case, there's literally 5 magnets sitting behind here. And for that reason, stronger magnetic field, we would expect it to have a further distance to reach that equilibrium. So this is the data that we're going to use, and what we're going for right now is to construct the exact test case that we see here, where we have a single anchor magnet and a single float magnet. We want to be able to place them 22.4 millimeters apart from the centers and see if we get this 32 millinewtons of force at that distance. And if not, we're going to use a material tuning process to dial down or up the strength of the magnet to reach that condition. So I'm going to start with where we left our project off. Task 1 is complete. I've already saved the project. I'm going to highlight task 1, right click, copy it. Now I click on the top level project name and make sure that that's highlighted. And I'm going to right click again and paste. So if you follow that process step for step, you should already have it named exactly what you want, task 2. So I'll pause and give you a second to get caught up on here, and then we'll move forward. Now what I'm going to do is delete the field overlays for now. So I just clicked down into field overlays and I highlighted B, and I'm going to delete them. We're not going to worry about those at this moment. Remember, this is in task 2. We're not doing any of this in task 1. It's also important as you operate to be conscious of the fact that the highlighted design type is the one that you are actively in. Sometimes you can confuse yourself into thinking that you're making changes in a different design that's actually not active. So we know that we're in the right one right now, and we're not going to mess anything up that takes place in the previously solved task 1. So what I'd like to do now is set up a second coordinate system. I'm going to highlight the region, and remember, there are ways to hide and show objects. I'm in the Draw tab right now. With the thing that I want hidden already highlighted, now all I have to do is click in the second row. It says Hide or Show Selected. I only have the region selected, so when I hit the X mark, remember, I'm not deleting, I'm just hiding. I can get everything back by hitting the master green check mark up here, and I can just repeat that process to hide the region. Well, the only reason I did that is because I just don't want it to interfere with things that I'm selecting along the way. So this is going to be our float magnet. We've already named it so. If you remember, the test that we're trying to reproduce is going to have an anchor magnet directly below it and also offset. And we're going to choose that to be the X direction. So just by a convention of our choosing right now, we're going to say this is the orientation that we want X to basically equal distance pointing up. So the force of gravity, if we were to simulate that, which of course we're not, would be pulling in the negative X direction. So with that, I know that I want the anchor magnet to be below this plane, the same as the thickness. So let's create the coordinate first, the coordinate system first. I have float defined. I'm going to choose global because I want the new coordinate system to still reference global. And then now I'm going to select offset origin. And just like I did before, I'm just going to choose that 0, 0, 0 location right there. And you should see it turns to a sphere, indicating that it found some sort of center of a geometry there. And remember, when I go and click on the new coordinate system, I can see, sure enough, it is at the origin. It's referencing the global. If yours doesn't look like this, go ahead and pause the video and make sure you get it to agree. I'm also going to change the name, like I did before, and call this one Anchor 1. Anchor 1 CS. So that's my first anchor magnet, and I haven't created the magnet yet, but I at least have the coordinate system. Now so what I can do is I can just maneuver this so that I can probably just create from scratch. There's a couple of ways to do this. I'm not going to use the duplicate commands. You've seen me do that in class before with draw. We have these move and move along commands. I'm just going to create one from scratch right now. And you'll see it really doesn't matter the way you do it right now. But I'm going to click cylinder, draw cylinder, and follow the same instructions before. Enter the base. Notice I'm on the bottom side of the float magnet, and I'm going to choose that point, and then I'm going to let the interface hopefully find an edge of the geometry. It looks like it's snapping to an edge, or maybe not. It looks like it's not snapping the way that I thought maybe it would. But in this case, if I stay along, it looks like one of the main axes. So I can see here along the y-axis. It's actually giving me an indication that it sees an edge here. So if I click that, that was my radius defined, and now I can go out. If I can make it to 3 millimeters, I'm going in the opposite direction here, and it looks like I just got it. So that's a perfectly stacked magnet. Remember that we never measured this condition. I'm about to do some offsetting here. So before we do that, go through. You'll notice that the cylinder 1 is the new name. This thing is going to be our anchor magnet. I'd like to change the name. I'm going to go ahead and call this. Sorry, if I click on the top level, cylinder 1, I'm going to call this Anchor 1. Okay, and you should be able to verify the values are the same. Of course, I've got a negative height because of the way that I built it, but that's okay. It's just keeping track of the direction. It should look just like this. So radius, and keep in mind that it's actually on the anchor coordinate system. What I can do is a nice little trick now that I already have the material defined for the float magnet. Let's go ahead and literally drag and drop this Anchor 1 into this into the same material heading for neodymium. So now just by dragging it and moving it and dropping it on top of that icon, I can see that they're both assigned to the same material. So that's exactly what we expected. So this is a great place to pause the video and get caught up. Make sure you see something similar to what I'm looking at here. Otherwise, I'm going to get moving, and we're just going to literally move the floating magnet now. So what I'd like to do, since if you remember, the float magnet, of course, is connected to the float coordinate system. One nice feature is that when we move the coordinate system, the object will move with it. So, for example, if I just select the coordinate system, and if I come down here, and what did we say? X is going to be the up direction. So if I orient it this way, so that Z is sort of pointing out towards us, out of the monitor, X would be pointing up. And now if I just come to origin, and let's just say I change it to 10, well then the center of the magnet has moved up relative to the center of the base magnet, which I should say the anchor magnet, which is also at the global origin. It's moved up 10 millimeters because that float reference is the reference of the global coordinate system. So the difference between this origin and if I click the global origin, the distance is it's now 10 millimeters in the X only direction. And so this is going to be the case for everything going forward with different coordinate systems that we add. So you can always remember the reference to the coordinate system that's hidden in the property, and we can always change it by literally typing in the properties field here. So what I'm going to do now is, if I remember back to the document, our test document, the test case that we were looking for is going to be at 22.4 millimeters. That's between the centers. So let me change that 10 millimeters to 22.4. This should be the exact condition that we ended up with the average of measurements on. Of course, what's not being shown is the foam board and the plastic and the ruler. All of those objects are expected to not contribute to the magnetic field and the forces whatsoever. So it's probably a pretty safe approximation to just remove them completely. So that's good. We have the magnet now at the appropriate distance. And what I'd like to do next is create parameters so we can get a direct measurement of force. So if I right click on parameter, actually before I do that, let me select the float magnet. Now if I right click on parameters, it'll give me these options of assigning force, torque, or matrix. We want force, and we're going to call this force float and keep everything else the same. And we will do the same for the anchor magnet as well. So I'm going to choose the anchor magnet, and I'm going to right click parameters, assign force, and this one, since it's the only one highlighted, is going to be anchor. And just like the other options with mesh options, I should say assignments, you should always be able to come back to the parameters and verify that it's highlighting what you think it should be applied to. So we're good with that now. Speaking of mesh, there is something that's changed. We originally had a mesh assignment on one object. If I right click to select assignment, the only object we had was the float magnet. Now we have the anchor magnet. So we also want the mesh operation to apply to that as well. So what I'm going to do is, with this highlighted, I'm going to highlight the other one, and now I'm going to right click and say reassign. And just like that, to verify, if I come back and click this again, and now if I ask it to select the assignment, then I can see both of them now have the mesh operations, the same mesh operations. So it's a very important step to the process. So make sure you go ahead and pause the video and get caught up to all of these operations. We should be all set. I'll go to the simulation tab now. I believe I've covered everything. I'll hit the validation button and everything comes up green. So I'm going to go ahead and say analyze all, and just like before with task 1, we should see a history start to build out on this task 2 in the message manager while it goes through similar calculations, this time of course with the 2 magnets. So I'll pause while this solves and come back while so we can talk about the solution. So after about 2 or 3 minutes, we're back to where we were before, just with the, of course, with the new model. If I go to Results tab, I can go to Solution Data, and I can go to my Convergence tab. I can see my delta and energy. If I go to Plot Form and change it to delta energy here, um, again, I want to see the final value to be below 0.1. So this appears to be good. I don't see any error messages here. So that's all positive. What I want to do now is plot. I'm not going to worry about the fields this time. We might come back to it at a later lesson. I want to get right to the force calculation. And if you remember, back from our measurements, we should, in this condition, we have the one stack anchor magnet, and our average distance was 22.4 millimeters. When they are that far apart between centers, we should be calculating a force of 32 millinewtons. And now we can get this directly from our simulation model. So now what I'm going to do is go to Results, and I'll go to 2D. Let's do Stacked Report. And you'll see I've got these categories, and I've got force as an element now because I made that a parameter. So if you can remember the direction that we chose, force, of course, is a vector, and we set this up so that the only force direction we would expect to see between these two magnets is going to be in the x direction. So they're equal, they're equally opposed to each other. In our test, we designed it so that it was limited to just one axis. So we're really only measuring one component of the force, and not the magnet. Probably a better way to say it was that we only want to see the x component because that was all that we actually measured. Okay, so with those two selected, I've got the force on the anchor, the force on the float, and I'm going to leave the functions section alone. So pause the video, make sure you get these settings the way that you see them, and as soon as you do, I'm going to hit New Report, and we should see from our stacked, we probably could have chosen table. I'm actually going to undo this now that I think of it. Let me go ahead and delete this, and now I'll go ahead and choose Report, and I'm going to do Data Table instead. So let's do the data table. Same thing, we'll force, and then we'll choose the x directions for both, and that should be better. I think it's easier for us to analyze. I'll close this out, and I can see here these are not identical, but they're very close. So we can probably explain this away as some numerical error that is causing that very small difference. We're not worried about the x number in this case. We moved our coordinate system so we know that we're at the right distance apart. So this only applies to the distance that we had that we had defined. So one thing you'll notice is that we're what you would call an order of magnitude higher than what we would expect to have measured. So instead of getting 32 millinewtons, we're getting about 300 millinewtons as the force. And of course, they should be equal and opposite to each other. So this all makes sense. I want to change the material value to correct for the material to more accurately mimic these magnets than the ones that were available in the database. And that's the next step that we're going to do. We're going to change the material value, rerun the simulation, and see if we get agreement then. Now in class, we went through an exercise where we came up with a number of trial values for this magnetic coercivity. And we tried different values in real time to see if they made a difference. And what we found was that there was one value in particular that seemed to get us very close to the result. So this is a worthy exercise in and of itself. We're going to bypass that for now, and I'm just going to go ahead and spoon feed you the fact that this number here, if we replace it in the vector value for the magnitude, that's all we really have to do, and we're going to rerun that simulation, and we should be able to match what we actually did in test. So I'm going to go back into our model here, and I want to change the value for both magnets. They're really the same property. So as I go and choose property here, the table comes up, and what I'm going to do is make sure that you choose the NDFE30. It should be highlighted right away. It's the one that's in the project. And instead of hitting view and edit, what I'm going to do is clone the material. And when I click that button, it's going to ask me if I want to change the name. And I'll go ahead and call this, you could really call it whatever you want, but I'm going to call it tuned value. Okay? And with that, I'm ready to actually replace the default number here. So it was negative, I believe, 265,000. Everything else is going to stay the same. And again, we did this by trial and error in the class, so let's just go ahead and use the information that we know of. So the existing system model is still there. There's another, the previous version for the project is there. So this is the one now. We want to use the one that's called tuned. And I'm going to say OK, and you should see it shown here. So both magnets now belong to this tuned. So remember, we didn't change the distance. These results have been X'd out. They're stale results. That means that if we rerun the simulation, it should update them for us. So we're at the right position, which is 22.4 millimeters, and now we have what we think is going to be the appropriate tuning of the material. So I'm just going to go ahead and simulate again. So go ahead and do that process while I pause the video, and we'll see if this force table has updated to values that are closer to what we expected. Okay, so after a few minutes, again, our result is updated, it looks like. These are no longer X'd out. I'm going to just double click the force table. And sure enough, it's very close to what we measured. So probably within the margin of error, if we took the time to calculate that, all of a sudden, just by changing that value, we're down to roughly 30 millinewtons. And the value that we calculated was 32. So we're going to say that's close enough for what we're trying to do. We're okay with that level of accuracy, and it should enable us to kind of move forward into the remaining task as we go. So that's it for task 2. Make sure that you save now. At this stage of the lesson, you should have one project with 2 design types that are in it. And as you've already guessed, when we move into the next task, you'll be creating a task 3 design here. So please make sure you save as you go, and we'll see you at the next lesson.